The Mandelbrot set is a fractal which can be computed by recursively iterating a function over each point in a complex plane and seeing if the function diverges to infinity, plotting each point depending on how many iterations it took to diverge or reach some predefined iteration limit at which you are fairly certain the function will not diverge further. The goal of this project is to develop hardware to graph the image as quickly as possible with efficient hardware. My system is parameterized and easily expandable. It lets the user fine-tune the final binary file to maximize the usage of available resources, leading to faster processing times. The system as a whole is made of three main parts. First, the iterator, which takes in the initial parameters such as the image resolution, the desired upper and lower bounds of the area to be calculated, and the maximum number of iterations for each point if it does not diverge. Next, the series of processing cores, which calculate each point. They are fully pipelined to utilize each element as much as possible and have a small amount of dedicated FIFO memory to handle back pressure from the following stage. These cores can be daisy-chained to work in parallel. All data widths, which affect the maximum resolution and size of the circuit on chip, can be easily adjusted in the MATLAB environment. And finally, the collector. Since the amount of time each point takes to process varies significantly, the output stream will be out of order and will need to be sorted. This is done with a small ring buffer where each point is stored relative to where it would be placed in the output data stream, using the lowest 10 bits to place it in the buffer. The output section continuously reads the current memory position it's at until it detects a non-zero value and then sends that value to the output stream. The buffer is split up into 4 segments of dual-port RAM to let it output a value each cycle while resetting the previous cells. The amount of space in the ring buffer that would be taken up by all points currently being processed is tracked to pause the iterator in case the ring buffer were to fill up entirely. The count is then lowered each time the collector outputs any data, making sure there's no clashes in memory. For interacting with the system, I wrote a simple Jupyter script setting all necessary registers and transplanting the resultant stream of data into an image. It also lets the user move about and zoom in on the plot. Here are the execution times in clock cycles for a 101 by 101 pixel image over 100 iterations using varying core counts. Worst and best case times correspond to 101 iterations per pixel, respectively, while normal shows the time for the topmost view. These results are simulated and do not include delays from DMA or other external components. Thank you for listening.